Hello again, everyone. So just a personal introduction. My name is Maurizio Rovaglio. I'm PhD in chemical engineering. I'm an ex-university full professor at Politecnico di Milano. I left in 2007 the academic environment to join the industrial one. I covered several roles, from operation to sales in different countries around the world, from the Far East to the Far West. And as you see now, I'm in Siemens, Italy, dealing with, as many of you, I guess, with digital solutions in the process industry. Today, the subject is something that we listen already in some way, but is, is very fashion, and I would say is almost a kind of buzzword, machine learning and predictive analytics. But we'll expand the concept from, let's say, data-driven to artificial intelligence. Here the agenda of the presentation, very quickly. I will start with a short introduction on the key concept and the philosophy of the predictive analytics that at least we follow in Siemens. Without going into many technical detail of the implementation and the algorithms, but with the idea of presenting more, as I said before, the philosophy and the approach, how we could improve, let's say, a pure data scientist, data-driven approach with more AI content. A couple of case studies where this technique has been successfully implemented, plus a video where I hope you can appreciate more than just in a slide the comprehensive and collaborative approach that is essential, is a key for the effective industrial application. At the end, a short recap with the main highlights. From these slides, just introductory, two main concepts. Nothing new if I say that to maintain production at the right level, we need to maintain the process equipment, which clearly, imply a significant cost. There is always a balance, between the what we produce and how we maintain the assets. Moreover, as we know today, is more and more difficult or almost impossible, to build a new plant, especially in the Western country. Therefore, there has been in the last year a growing attention to maintenance, and in particular, how the digital application can improve operational efficiency. And behind the digital application, I mean, digital means everything. Behind the digital application, we mean connectivity, analytics, and cloud. Lower cost of sensor, large availability of data, and the larger broadband connection. For this reason, many data-driven analytics solution has been developed to extract value from the data. This with the aim to improve the operation by more equipment availability, what we call uptime, and to improve the performances. The greater the process efficiency, the higher is the production. So pushing plant to reach more, what we need is to push plant to reach more than 100% of their design capability. Equipment predictive analytics is something today very attractive for all the industrial sector, but there are significant differences and also different results between the different approaches. So let's try to go into a little bit in the details of what is predictive analytics. Predictive analytics is typically based on historical data and through, let's say, various statistical neural network type of algorithm is possible to understand the pattern or the behavior of a specific variable. This is what we call, or is being called in literature, deep learning, and it could be identified actually as the first step of the equipment predictive analytics. If the algorithm is becoming adaptive, which means being able to adapt the model by new real-time data, and it will be possible to recognize new pattern based on the current unit behavior. This is what we call machine learning. Now, if we add, a new layer of artificial intelligence that is called knowledge-based or case-based reasoning, which enable the APA, I mean the equipment predictive analytics algorithm, to reason, to make choice by a database of snapshot of process condition, we can improve significantly the response of and related action effectiveness of the tools. But we will say something more also in some slide later. So just for showing something in details without too much details, but anyway, going through the main step of what we mean or what is the approach in equipment predictive analytics. Three main steps. First one is to identify the target sensor correlation. In a plant, there is around the unit we have a number of sensors, a huge number of sensors providing info about the equipment behavior. Depending on the focus objective that we have or the target we have, we should identify which are the output variable and which are the input variable to build the corresponding best APA model. Since the number of data normally is huge and the number of sensors is huge, we need to spend a lot of time in data analysis. Actually, it was mentioned already, and in the data cleaning or in data pre-processing. So we have two alternatives: or main power by data scientists, or smart tool with the capability to process all the data and return automatically a matrix of correlation, which allow easily to Hello, can you hear me?
That's okay.
Yes.
Yeah.
Okay. No, because I got a message that the host was muting me. Anyway, maybe it was a mistake. Okay. Okay. So once the model is identified, what is needed is to train the model. And as you know, any data-driven model, and this is important, based on statistic or neural network algorithm, can be used to predict only something that it learned. In other words, it cannot predict a unit behavior that wasn't presented to the algorithm through the historical data. Therefore, there is a need to select properly the data set to be used for the model to train again, and either again, or we spend hours by the data scientist, or we use a proper tool, proper user-friendly tool that allow the user to move in the ocean of info and select the proper one to create a reliable APA model. Once the model is designed, now we need to use for monitoring the equipment behavior and to predict fault and anomaly. There is no time now to go through all the details of how is presented in the slide, but it's important something to underline is that what is important to underline is the capability to create, through the tool, an intuitive dashboards representing a number of target sensors through simple and schematic type of plots. So providing the operator with a clear overview summary of the process condition. But anyway, despite the dashboarding, the APA tool based on the predictive behavior should also provide the alerts whenever a constraint or a threshold has been violated. So as we now, let's move to the what we mean with the artificial intelligence layer. So as mentioned before, a machine learning tool is based on a pure data-driven approach, and it has two main limits. It provides an alert without suggestion on remediation, okay, and it could be subject to false positive. This is something very important, which means that the alert could be generated from, let me say, numeric noise or bias, and if judged alone, it could bring to a wrong decision. So artificial intelligence can help to improve performance of the machine learning tools by what we call CBR algorithm, or case-based reasoning, or knowledge-based approach. This consists in capturing the know-how or the knowledge of experts and experienced people in a kind of data archive matrix. Each matrix will consist of, for each equipment, in a number of historical fault cases represented by the value of the sensor in that condition. So a snapshot represents the status of the equipment in that condition, with the corresponding procedures for the anomaly resolution. The CBR algorithm will compare the data coming from the machine learning with a snapshot in the data archive and reasoning among, let me say, the similar condition. It can provide validation of the possible alerts, in the same time presenting in advance the list of the action to be taken to resolve the potential fault. Let me say, modern tools of predictive analytics are also provided now today with the natural language processing capability. Typically, to easily, let me say, add new information to the status archive, or recall in advance specific status to be compared with the current process condition. Few examples now. Obviously, the key question, as we know, has been let me say, reported also from the previous presentation: are these tools working and reliable in industrial environment? Here following, there is a couple of examples, which I apologize, but for time reason, I will go through very briefly. As mentioned, especially in the oil and gas industry, new plants are more and more difficult to build. And for this reason, oil and gas is one of the main sectors that is trying, to squeeze the iron over the capacity. Key equipment for maintenance to avoid expected shutdown, the critical equipment typically are the rotating machine, like the pump, the compressor, the turbine. No faults means higher uptime, and so higher production. This is an example of how the equipment predictive analytics tool works in our case. All processes are clearly equipped normally, as we know, with control system and with a number of constraints and thresholds on the various parameters. For the conventional control monitor system, the issue is that once the alarm is generated, we are essentially on a no-return way, and the fault is going to happen. So the equipment predictive analytics tool must be able to predict the event in advance. And the slide shows that the APA tool was able to alert the operator about an unstable compressor output pressure 18 hours before the control system. This time lapse is what the operator can use to validate the alert first and take possible action to avoid the fault and resolve the anomaly. Not only the oil and gas or petrochemical industry is, not only for the oil and gas and petrochemical industry, the APA, the equipment predictive analytics, is relevant. Another sector, for example, presented in this slide, the cement industry. Here we have a big rotating and moving machine plus large flow of solid material. This could generate faults for crust formation, stack of material, creating plaques and blockage of the unit. The APA tool has been applied in this case to monitor the three main units: the preheater, the rotating kiln, and the clinker cooler. Here in the slide, we show the APA application that was able to predict with more than 2 hours in advance the fault alarm of the control system, which is given by the control system. The APA recognized in advance that this type of unstable inlet temperature, for the preheater, was causing or there was a potential, question of crust formation and leading to an unplanned shutdown. Again, the 2 hours, in advance allowed the operators to validate the alert, again, false positive possible, in case, and to follow the suggested procedures. Here, I'm trying to give you an overview, through a video, because, to be really adopted in industrial environment, this type of tool cannot be simply, mathematical tools managed by data scientists or domain experts. They need to be easy, user-friendly, and create a collaborative environment between multiple roles and people. And actually, they need to have, the capability to define or to, clean possible false positive. So this is a short video. I apologize because the video has been cut to avoid, to reduce the time and to avoid also the commercial part. And full video is available anyway, as shown on YouTube. And I hope everybody can hear the audio.
The focus on turbines in our petrochemicals division. In this example, the organization has 8 chemical plants scattered across a continent. KPIs are calculated for each asset and each type of production and are shown here. At this level, we can also see overall production KPIs and equipment health indicators at each facility, some production information, and even a list of bad actors, which allows us to go immediately to problematic assets. Let's take a closer look at the plant that seems to be causing the most trouble. At the plant level, we can see asset health by asset type, like exchangers, compressors, pumps, turbines, and so on. The portal gives us insight into many types of assets throughout this facility and combines basic engineering with sophisticated technical information from Siemens experts and other sources. We can look at pump data or heat exchangers. Back in the plant view, the health indicators have flagged an issue with the turbines. The overall health indicator looks good, but let's take a closer look at the turbine family. Here we see our fleet, sorted by health index. It looks like all 8 are running. The first one on the list, an SGT800, appears to be having problems. This turbine is running, generating power. It does have a failed start in the last 30 days and several alarms. Our condition monitoring application has raised an issue involving lube oil pressure. Based off this information, this is likely our bad actor and the one we need to investigate. Now we're at the level of an individual asset. The left panel shows conditions that have been raised. At the top of the list is our lube oil pressure. That's the newest condition, and it has not been acknowledged or worked by anyone. So we'll focus on that one. Our advanced analytics analysis suggests checking instrumentation for false alarms and for a plugged filter. This overview screen shows some overall performance indicators and key process variables. When we look at the maintenance view, nothing interesting comes up. There's a history of inspections on the lube oil system, although the most recent one was several months ago. Here we also see some failure modes. We may want to look into that further and see failure modes related to the lube oil system. As we scroll down, we see the lube oil piping fatigued, potentially a critical error, along with some failure facts and recommended actions. With the engineering view, we can see documents, parts inventories, and some design information. Let's take a look at the documents we have.
Yeah, just to some few notes in conclusion to recap. So the first point is APA approach require efforts, as we mentioned also in the previous presentation. It's not something that is coming for free. The APA provide alerts, but with no knowledge. So we need to have something that will transform the alert in recommendation or in a solution. Okay. The artificial intelligence knowledge-based algorithm can definitely improve, and facilitate the APA type of tools and use. False positive is a key and must be addressed. In terms of industrial, whenever for an alert there is a decision that needs to be taken, then there is a need also to be sure that the action or whatever is the action and the procedures to follow will be based on robust type of information. Significant improvement anyway, a large improvement can be obtained using this type of technology. So thank you very much, and if there is any question, I will be happy to answer.